lecture, just so we can save time. This is a lengthy and heavy lecture to get through. Okay, let's go. All right, so we'll be going over.
Okay, well, first of all, this is the motors and encoders lecture.
So yeah, we'll be going over first of all, what the different motor types are, and then how do we get to actually controlling the motors, such as the spin direction, and also the power that we supply to the motors. That way we can get different speeds. And then we'll finally get into encoders, which measure the amount that the motor shaft turns, and thus we can track distance that the robot travels.
Okay, so first let's take a look at the different types of motors that we're going to be choosing for Micromouse. So, what are motors, first of all? Motors are just devices that turn electrical energy into rotational motion. There are two different types of ways to power motors, and like the two different types of currents that you can use to power them are direct current and alternating current. We'll go into a little bit about what each of them are a bit later on. And there's two main types of motors. There's brush motors and there's brushless motors.
And we'll go into these types in the coming slides. Okay, so to begin with, brushless motors. So the form of power that they take is AC current, and this stands for alternating current, and DC stands for direct current. And a common source of AC power is just from the plug or the outlets in your home, or just right over here. And the pros of them are that they are more precise and have greater efficiency for brushless motors, but they are expensive and much harder to work with because you have to convert. Because you have to do the conversion from DC to AC because our batteries only provide direct current. So in order to run a brushless motor, which takes AC current, you have to do the conversion, which then also takes space and thus weight. And some common applications are in electric cars, like all electric cars use them. And then also in RC motors for like RC planes, cars, those kind of things.
And just to like go over kind of how brushless motors work, is that there's a magnet in the middle that's able to spin, and it's surrounded by several electromagnets around that central magnet. And the way that it works is that like you send or you turn on and off the electromagnets around the central magnet in such a way that like it spins the inside magnet.
So for example, when this one is on south and when the south pole of the magnet was over here, it would repel the south part of this shaft and thus force it this way. And also it works by using attraction. So when the north pole is here, when the south pole is more over here, it will attract the south pole towards it, thus causing it to spin. All right. I don't have to know too much about this because this isn't essential to Micromouse. We just thought we would go over the physics anyways.
And then the second type of motors that we're going to be going over are brush motors. Now these are a lot simpler than brushless motors to understand and to use. Some of the pros are that they're really cheap, they're easy to use, and they're simple. And some of the cons are that they're significantly less precise and less efficient. Now, the way that the brushless motor works is that it just takes direct current, and in the motor itself, there's like a loop of wire through which the current is sent. And if you've taken like physics 1B or 1C, if you haven't already, it's fine, you'll take it eventually. But the way that it works is that when you send a current through a loop of wire, it creates a magnetic field through the loop. And inside the motor, there's like two bigger magnets surrounding a loop of wire. And essentially, when you send a direct current through this wire, it creates a magnet, causing it to attract to the two outer magnets. And when it attracts to the two outer magnets, like the poles or the two leads of the wires switch, which means like the current will start flowing from one direction to the other direction when it spins. And like this keeps happening repeatedly, which causes it to like continuously spin and like repel the two outer magnets.
And the most important thing to remember just between these two different types of motors is whereas the shaft of the brushless motor, of the brushless motor is the permanent magnet with the electromagnetic coils helping it spin and changing the magnetic pole. The shaft in this case is the electromagnet which changes the poles, and the permanent magnets are on the outside.
Does anyone have any questions before we move on? Because this can be kind of hard to understand. All right. Or never mind.
Okay, so again, here's just some common examples of brush versus brushless motors. I don't have to really get into them, let's move on.
Okay, so now let's get into the specific motors that we're going to be using in Micromouse. So the general specs of the motors, okay, so first of all, this is the picture of the motor that we're going to be using. When you get your rack kits, you'll get 2 of these, and like they're a lot smaller than like this, but you'll see them eventually. Some of the specs are that they have a 30-to-1 gear ratio, which means that for every 30 times the motor itself spins, like the actual axle spins 1 time. And the reason why we do this is that is so that we can get more torque out of the motor. The ideal operating voltage is at 6 volts. This is kind of important. We'll get into that a bit later. And the maximum current draw is 0.67 amps.
But remember this figure for a question we'll ask later. So now going into motor control, how do we turn them on and off, control their direction, and then also their speed. So the components to controlling the motors, again, is just these 3 components. And I'll move on to it. So now for motor power first. Okay, so here is an incorrect diagram of how to control a motor. So this incorrect diagram, again, I should say, is the pin supplies power. So the pin, meaning the microcontroller pin, would supply the power of the signal. Here's the motor, and then here's ground. So does anyone want to guess why this is incorrect?
Microcontroller does not operate at 6 volts.
Exactly. So that's exactly why. Because so again, to say the ideal motor specs is that the motor requires 6 volts and 0.67 amps, whereas the maximum pin power is only 3.3 volts and approximately 100 milliamps, which is not nearly what the motor needs, and this will prevent the motors from being able to run at full capacity. So what is a solution to this problem? How can we get that 6 volts?
Use like a transistor.
No, but there's another source of power that we have.
Use a separate source of power?
Yeah, so what separate source of power do we have? Or where's our main power source?
The battery.
The battery, exactly. So if
Actually, you were correct. We do use transistors, but we'll get into that a bit later on.
the transistors are for a different purpose. So yes. So we would directly use the battery voltage.
Okay, so how do we use the battery voltage directly? Well, like someone said, we use transistors, and what transistors are they're basically switches that you can put into the circuit. And the way that they work is that each transistor has 3 leads: the emitter, base, and collector. And you can turn on and off the current flow between the emitter and collector by sending a current to the base. So we can take advantage of this by connecting our circuit between the battery and the motor to the emitter and collector, and connecting the microcontroller to the base. So whenever we want to let the battery power the motors, we just send the current from the microcontroller to the base.
Is there any questions about that concept of how a transistor works? No? Okay. And so,
Yeah,
what
to
should we attach to
reiterate,
the base?
yeah, so to reiterate, we just attach the pin output to the base, so like the microcontroller's pin out to the base, and then to the collector and emitter, we just attach the battery and the motor.
Okay, and so now for turning on and off the motors, so we can control the on and off state of the motors by using the microcontroller pin, sending a on or off signal to the base pin of the transistor, thus allowing us to control down and off state. So is there any questions about how this part works?
What's the MCU?
The microcontroller unit. So that's basically like the central brain of the robot.
Okay, so now we have this circuit where you have the battery, you have a motor, and you have a transistor that connects to the microcontroller and to ground. And this is an almost complete circuit because we actually run into a problem if we just use this circuit just as it is right now. So the problem is inductance. Basically what happens is that whenever we turn the motors off, due to back EMF, it creates like a large spike in current, which like is just sent throughout the circuit, and it could lead to the microcontroller pins shorting. So how do we stop the current? the current from flowing the wrong way, and we're gonna get into that on the next slide.
And also just to add, so essentially why is there a back EMF, or what even is an EMF? Probably a lot of you haven't taken 1B or 1C yet. So an EMF is an electromotive force, and so an inductance is basically, it's like in the name, a current is induced when the motor acts as a generator instead. So how a motor works is we provide power, we provide current, and that causes a rotation. But in a generator, a rotation occurs, and then that causes current to be produced, and then that's why we have a back EMF. So does that make sense to everyone? Okay. And what circuit component only allows current to flow one way?
Diode.
A diode, exactly. So we can use a flyback diode to prevent the current flow from going in the wrong direction. So as we can see over here, the battery, the current can flow from the battery to the motor, but when the motor produces the battery can flow through the motor all the way down to here, but then when the motor produces a back EMF, it will prevent it from going down this way.
Okay, so just before we move on real quick, a little bit more about transistors is that internally they are technically an on-off switch. However, they can be used as a lot more than just on-off switches. They can also act as variable gates if we use PWM signals on transistors, which we're going to get into in just a little bit.
And so basically, now we're going to cover motor direction, now that we have covered how to do the on and off states. So now for motor direction. So this is the expanded version of how we can control our motor direction using two sets, or I guess you could say 4 sets of the circuit that we saw previously. So it's 4 transistors and 4 flyback diodes, and we'll explain how this works. So what happens if we turn on or pass power to Q1 and Q4? And we leave Q2 and Q3 off. Does anyone want to take a guess what will happen? Which way will the current flow? Is the question for If the answer just got leaked, does anyone want to just say it?
The current goes right through the motor.
Exactly. There we go. Yeah, so the current goes right through the motor. And then for the next part, so what happens if we turn on Q2 and Q3? But leave off Q1 and Q4.
Goes left through motor.
Exactly.
Okay, so just to explain this a little bit, I think that might be a bit confusing to some people. Basically what this diagram is that it allows us to change the direction in which we send the current through the motor. And since we're using DC motors, the way that we change the direction of the motor's spin is just by changing the leads on the battery. So if the current is flowing one way through the motor, it will spin in one direction, and if it's flowing the other way, it'll spin in the opposite direction. So by having 4 transistors and this specific diagram, if we turn on Q3 and Q2, for example, it'll only let the current go from the battery through the motor in one direction, whereas if we turn on the other 2 and leave the other 2 transistors off, it will allow the current to flow through the motor in the opposite direction. And if we do this, we can basically control which direction the motor turns in by just using 4 transistors. Does anyone have any questions on that?
Yep.
If we mistakenly turn on Q1 and Q2 to be short.
Yeah, exactly. So if we turn on Q1 and Q2 or Q3 and Q4 or just all 4 of them at once, you will short the circuit. So please do not do that.
So now that you already answered that question, if we turn on all 4, don't do it. You're going to short the entire circuit.
Wait, did you also have the question?
Why do you need 4 flyback diodes if there's only 2 modes of operation?
Okay, so each transistor corresponds to 1 flyback diode.
So I can go ahead and explain it. So if we have power from the very top, so if we turn on Q1, and are you kind of asking why don't we have I guess it's a single wire somehow?
Why don't we have 2 diodes instead of 4?
Because we're going to be using all 4 of the transistors at some point.
Oh, okay.
Yeah, so you don't only want your motors to spin in one direction, right?
Yeah.
So if we let's say Q1 and Q4, if you only use those two, your motors will only go in one direction.
Oh, okay.
But like if you want to use the other two, you're gonna need the other two flyback diodes as well.
And also really quickly, so if you're wondering why if we only turn on Q1 and Q3, Q1 and Q4 will the current not pass through Q2? It's because first of all, the base pin would be off on here, so that's preventing current from flowing through this path. And then since we have a diode right here, which only allows current flow this way, the current also won't pass through this path. So the current will not have to be forced to take this path over here when the base pin would be on, thus allowing current to pass through and to ground. Does that make sense? We can go over that one more time if anyone has any.
Can you explain again why the diodes are necessary?
Can you go to the previous slide?
Yes.
Yeah. So basically what happens is like inside the motors itself, there's a lot of spinning magnets, right? And what happens is like when you just like stop giving the motor power, those magnets slow down. And if you have like magnets that are spinning and decelerating or accelerating, it creates a current through the wires. You're gonna learn about this more in your physics classes, but that's what's called a back EMF when the motor stops spinning. And to prevent that EMF from like going into the microcontroller or like harming the other ICs on the Micromouse, we have the flyback diode, which forces any back EMF like to go back into the battery so that doesn't like harm the rest of the circuit.
So like here the diodes in parallel with the motor, but in the other schematic it wasn't. So,
So
when would current be flowing through the diode in this?
Yeah. So in this schematic, like, okay, let's say Q1 and Q4 are on and like it's going this way, right? Like the current is flowing left to right. If you turn off the motor, any back EMF would just get sent through this diode into VCC. And similarly, if there is any back EMF here, it would just like go into VCC as well, like back into the battery instead of like to the rest of the circuit. Does that make sense?
All right, so okay, moving on. We have like a long lecture ahead. So now we're going to go over what the dual H bridges are. So these are what will actually so this entire thing that you see right here is now condensed, or I guess maybe not condensed because of a lot of inputs, into this thing right here. So we'll go over it right now. So this can control two motors. There are four inputs, two for each motor. So Q1 and Q3 are grouped. So of course, if you want to get the motor to spin one way, you would turn on Q1 and Q1 and Q4. So that's why you would that's why you only need one pin to control the motor to spin one way, because you can turn on Q1 and Q4 simultaneously, and then you can also turn on Q2 and Q3 simultaneously to get the motor to spin the other way. So we don't need two separate inputs for Q2 and Q3 or Q1 and Q4. We would just combine them into one. So and then we also have four outputs, two for each motor, and each output controls one direction, and they also have enable pins, which allow the motor to operate, because we don't want to accidentally send a signal or accidentally send a voltage or power to the motor. So these enable pins prevent you from accidentally sending power when you don't want to send any power. Are there any questions about this? That is definitely confusing. Yep.
How does the enable work exactly?
You just pass in like on or off, like 1 or 0. Yeah. Are there any other questions? Yep.
So you were saying one input controls two, like Q1 and Q3, then why we have 4 input?
Oh, so this IC is actually just like, remember like the big schematic that you saw before? It's like two of those combined into one chip, so that like you can control both your motors with just one chip instead of needing like multiple circuits. So if you go next slide, like I think input 1 and input 2 will correspond to like one motor, and output 1 and output 2 will just like go to that motor. So it's just like a chip in which there's like two H-bridge schematics like packed into it.
Oh, sorry, I didn't understand what's the relationship between enable 1 and the inputs.
Oh, okay. So there's no like relation between them. Just like for the first H-bridge to work, you just need to like send a constant 3.3 volts to the enable pins. Yeah.
Basically, the enable will actually allow the inputs to be passed on into the outputs. Otherwise, it would just be completely off.
Okay.
Yeah. And just to again elaborate, so we can condense this input and this input into one input because we will never just turn on Q1 and not Q4. So we will turn them on simultaneously, so therefore we can have just one input for 2 and then one input for 2. And since we'll have 2 inputs for each motor, and since this controls 2 motors, 2 times 2, 4 inputs.
Any other questions? All right. And you're going to be making this in your assignment, but this is like the schematic diagram for the dual H-bridge chip that you saw. And like in the schematics, you'll see things like, oh, the 3.3 volt constant inputs to the enable pins, or like these microcontroller pins that can send signals to the inputs, and like the output pins being connected to the motors. And then in addition to that, there's also a set of decoupling capacitors, and they're basically just to make sure that the motors get a clean signal instead of like varying voltages.
And if you're wondering what, so VS is the main power supply to the IC. VSS is, I'm pretty sure, is the power supply to control the logic gates within the IC, which you don't have to worry about. We still have to supply power to them. And these are how some physical H-bridge ICs look like. So you can have these very chunky versions right here, or you can have the much smaller ones, the ICs that we will use right here. And this is a mouse. Okay, it's a mouse. Okay, so this is the placement of the IC on our wrap designs. Okay, so now we've covered motor direction.
So right now, all we've covered is like how to turn on and off the motors and how to change the direction of the motor. We really haven't talked about how to change its speed. So the way that we tell it to change its speed is through this thing called post-width modulation, or PWM signals. So essentially the way that this works is that instead of just like telling your motor to stay on for like a long period of time or turn off for a long period of time, you like constantly keep turning on and off the motor like really, really fast, like thousands of times per second, so that like it's not going at full speed, but it's also not like completely at a stop. So like the inertia that the wheels have when you turn it on and off will just like keep carrying it through when it's off. And to go over some terminology or like some key terms that you might need, the duty cycle is the percent of time in which like you're sending the on signal to the motor, and the frequency is the number of cycles or like the number of on and offs you have in every second. Does anyone have any question about this? Yes.
So essentially, you're just like controlling how long it's on, like, or controlling the length of pulses in order to control the voltage of the motor.
Yeah, exactly. So if you want it to go faster, you'll leave it on for a longer period of time, let's say 75% of the time. And if you want it to go slightly slower, you only leave it on for 25% of the time.
And if you're wondering, so of course frequency depends on the number of cycles per second, and the cycles per second a cycle is defined by the period. So the period is defined by just one segment of on and off. So this is one period from here to here. And this is another period, and keep on going on. Are there any questions about this? Yep.
So are you setting the frequency before like you're determining which duty cycle to use? They're not like depending on each other, right?
Yeah. So you do set the frequency that you want to use beforehand. And we'll go over that in like the next few slides.
And it's kind of like an inaccurate way of thinking of this, but if this kind of helps you understand like why we do all this on and off. So if the output that we can normally provide is only 5 volts, and the off is of course 0 volts, but you want something in between. So you can then have a duty cycle of 75% where you're supplying 75%. So you're supplying 5 volts 75% of the time, and 25% of the time you're not providing any voltage. And this will then create a 0.75 times 5 output voltage, so which is 3/4 times 5 volts, which is 15/4, which is I don't know. So hopefully that makes more sense to everyone? Okay, cool. And so now we want to, so now we can just cover like the frequency and then how we do these different calculations. And so the MCU clock speed, which is like, I guess, like how often it counts or how fast it counts, is 16 megahertz. And then the H-bridge, the maximum frequency that it can accept is 5 kilohertz. So our counter period, or rather how many counts exist for one period of the duty cycle, is just simply 16 megahertz divided by 5 kilohertz. And that gives us 3,200 clock cycles per period. So again, that's 3,200 counts per period from here to here. So for 75%, so for a 75% duty cycle, for 75% of the 3,200 clock cycles, we'll have an on signal, and then for the other 25% of the 3,200, we'll have an off signal. Does that make sense for everyone? Okay. Yep.
What if you try and use a higher frequency than the max frequency of the H-bridge?
It just won't work properly. Like,
Why?
well, okay, so you know how like you're turning on and off the transistors really, really rapidly? There's only like a certain, or the transistors can, or like the transistors in the H-bridge can only handle a certain speed at which you turn it on and off, and the microcontroller operates on a much faster speed than the H-bridge can handle. So if you just like turn it on and off a lot more, it just like might not turn it on or off.
Also,
If
I
that
assume
makes
it's
sense.
less accurate too,
Yeah.
because you have less counts per period, so that you can achieve like a more fuller range of values.
Could you explain again how you got the counter period?
Yeah, I can do that. So the microcontroller itself operates on 16 megahertz, or a 16 megahertz frequency, which means that like it can send up to 16 million, if that's what mega stands for. I don't remember, but like it can send like 16 million pulses per second, whereas the H-bridge can only take up to 5,000 pulses per second. And we can't really like send all 16 million pulses because the H-bridge won't be able to handle it. So what we do is that, instead of sending 16 million, we're just going to divide 16 million by 5,000 to get 3,200 clock cycles, which is the amount of time that the microcontroller takes as one full period. So like one full on and off is 3,200 clock cycles, so that it can like match the 5 kilohertz frequency of the H-bridge.
Okay, so you're just telling the microcontroller how long to wait before sending out the pulse?
Yeah, so kind of. So you're telling the microcontroller the length from like an on to an off. So like it can be different amounts of time on and different amounts of time off, but in total it has to be 3,200 clock cycles.
So it's not waiting; it's just dividing it. It isn't dividing it into continuously adjoint waves.
So you're like stretching it out in order to. Okay.
Yeah.
Okay. Thanks.
Also, just think of the H-bridge max frequency as just like the amount of waves or periods it can accept per second. And so if you have a 16 megahertz MCU clock speed, you have to somehow convert that into producing 5,000 waves per second. So if you have 16 million values, and you can have 5,000 waves per second, that means that 3,200 values should be per wave. If that helps people, if that helps you guys understand that.
What happens if we do use like a slower clock cycle? It's just less responsive. Is there anything bad about it?
No, you can use a slower clock cycle if you want, but I think it has to be like a multiple of 5, or it has to be like 16 megahertz divided by n times 5 kilohertz, because it might, like if it's like some weird number like 3,201, it might like, actually, no, it should work. Yeah, it should work with just like anything more as well.
Also, with a lesser frequency, you would have greater delay in changing your values because if you divide by a lesser number, then you would have more clock cycles per period, and thus you would have to wait for a longer amount of time to then adjust your value. But it's like a very minimal amount of time, but it is something to note, I guess. Any other questions? Okay.
Alright, so now we've gone over how to turn on and off the motors, how to change its direction, and how to like control its speed.
Any questions about any of these three topics? I know there's like a lot, so. No, okay.
Okay, so right now, like you know how to turn on your motors, you know how to like move your mouse, but your mouse still has no idea where it is in the maze or how much it's actually moved, and that's what we're going to cover next. So we're going to be going over encoders, which allow your mouse to know exactly how much each motor has moved, and then like based off of that fact, you can figure out where the mouse is in the maze, or how many cells it has moved, or like whether it's turned or not. So, alright, so what encoders are is that they just continually measure how much the motor has rotated over and over again. And they give us a way to tell how far each motor has traveled. And like there's two different types of encoders. There's optical encoders and magnetic encoders, and we're going to be going over how each of those work right now.
Or just how the magnetic one works, but there does exist the optical encoder.
Okay.
So the magnetic encoder, so they sense the change in rotational position as the motor spins by using magnets and sensing the magnetic poles on this magnetic disc right here. And this is the actual encoder circuit or attachment that you can put on to your motor on the back, as you can see right there. So this is a 6-pole magnet disc with 60 degrees between each of the poles, north and south alternating. And we also have 2 Hall effect sensors on this encoder, which can detect these north and south pole magnets. These are permanent magnets, I should note, that are put directly onto the motor shaft. So this magnet will literally spin as this back shaft spins, and then this attachment is stationary, so this can measure the amount of times these north and south poles pass by these 2 sensors right here.
So yeah, like with the magnet spinning in the back and the encoder, it can tell based off of how many north-south poles have gone by, like how much the motor is actually spun.
So here's an example of it actually happening.
Yeah, so you can think of this as like the back of the encoder with the magnetic disc and like the 2 Hall effect sensors. And the way that it works is that as the motor spins, the magnet also spins, but like the 2 Hall effect sensors stay in the same place. And like if you like look at the math, each pole is 60 degrees apart. The Hall effect sensors are angled 90 degrees from each other, which means that every around 30 degrees, you're gonna get another encoder, or like a change in the encoder values. So basically what happens is that like based off of whether the encoder or based off of whether the motor is spinning clockwise or counterclockwise, the encoders can actually tell which way it's spinning based off of the phase of the signals. So let's look at the clockwise rotations first. Basically in the clockwise rotations, the first thing, actually can you like go back? Yeah. So as you can see right now, Hall effect sensor 1 is looking at a north pole, whereas sensor 2 isn't really looking at any real pole. So it just measures the north pole. And then after the motor has spun a little bit, the second sensor can detect the south pole, and this just like keeps on happening as the encoder rotates. So you can see like the north, south, south, north, north, and it just like keeps on going as the motor keeps rotating.
And it's important to start that we started with north, and this will determine the clockwise direction.
Yeah. And then if, however, the motor is spinning in the opposite direction, the sensors will detect a different order of north and south poles. And like this difference in like the order in which it's detected is called the phase difference. And based off of that, you can tell which way the motor is actually spinning. So if you can, as you can see in the clockwise rotation, you have sensor 2 detects sensor 1 detects a north followed by sensor 2 south, whereas in the counterclockwise rotation, it's a north followed by a north, and like that difference is what allows your encoders to tell which way the motor is spinning.
Are there any questions about the slide? Yep.
When we implement the encoders, do we have to deal with the stuff in the table, or is there like already an abstraction where it just tells you the ticks?
Yeah, so you don't actually need to implement all of this in code or like worry about, well, it's good to know how it works in case like something goes wrong so that you can like debug the hardware. But in the software itself, like STM boards already have like built-in features for encoders and stuff. So you'll just like straight up get the counts based off of how much the motor spins. Any other questions?
Okay, so let's go over the encoders. So as we said, the encoders count one count every 30 degrees, and that means we have 12 counts per full motor rotation because they're 360 degrees in a full rotation, of course. But something important to note is we have a 30-to-1 gear ratio. So what this means is that every 30 times that the central motor shaft spins, let me just make up back to a picture of the motor, it might help. So every time this small central motor shaft spins 30 times, the big shaft on the output will only spin once, thus allowing for more torque and also for more precision from our encoders for every rotation. So going back to that slide. So this will allow us to have a full 360 encoder counts per wheel rotation instead of just 12, because again, every 30 turns of the smaller shaft makes one turn of the bigger shaft, which the wheels are attached directly to. And then the wheel dimensions are as follows, and then based on just doing some simple math of like, okay, what's the circumference of the wheel per rotation, we can then determine that we have 36 counts per centimeter moved of the Micromouse. And this will be very helpful when determining how many encoded counts to move forward per cell.
Any questions? Okay. All right, so you might be wondering how the encoders work with the microcontroller, and the way that they work is by using timers. So basically, there's counters that keep track of how much or like the encoder ticks, so like the number of poles, and based off of that, you can determine how many encoder ticks have passed. And in the software itself, you're gonna have, since there's 2 Hall effect sensors per encoder, each encoder is connected to 2 timer pins on the microcontroller unit, and these pins are what determine like how many, they can decode what the encoder is sending over to them.
And thankfully, STM has a library for that called encoder mode, which is automatically interpret those signals. And so as a quick recap, here's just how the system works. So we'll first provide power, we'll first provide a signal of how we want to control our motors to the H-bridge motor driver, which then sends the inputs to the motors. And then the motors rotate, thus causing a signal change in the encoders. And the encoders will pick up this, the rotation of the motor. And then they'll pass on their values back to the microcontroller, which we can then interpret it into encoder counts. That's just basically how the system works on a very simple level. Any questions about the diagram? All right. We won't do a demo today, but we will definitely do one. We'll definitely do a recording and put it on the Discord. And any questions? Okay. Are there any questions? Yep.
Wait, so we're depending on the accuracy of the wheel to determine where our mouse is heading?
You're determining, or you're relying on the accuracy of the encoders to determine where the mouse is. So, like, at the back of the motor, the encoders spin 30 times every time the wheel spins, right? And the encoders can tell, like, pretty precisely exactly how many ticks have gone by. And, like, based off of the encoder values, you can tell how much the mouse is moving. Obviously, like, it will lead to problems if your, like, wheels are skidding, right? Because your encoder counts will just go up without the mouse just moving. But there are ways to, like, get around that as well by using acceleration to prevent skid and stuff like that. Any other questions? Yeah? Okay, so about the rack kits. We're done making your teams. We'll release it right after this lecture. And then after that, you can, like, get together with your teams or just, like, come to the lab anytime this week to pick up your rack kits. And there's going to be a work session this Friday, so even if you're not able to do it this week, you could just, like, come with your team on Friday to the lab, and then you can, like, get started on the assignments.
And we're dropping assignments 2A and 2B along with 1A tonight. Don't worry, we're giving you guys plenty of time to get these assignments done. We have, like, a 2-week break until the next lecture. And this Friday we'll be hosting a work session in the IEEE lab, 2825 I believe is the room number to the IEEE lab in Boulter. And please show up because Martha and I will be there to help you guys out, help do all the soldering, help do the coding. And these are what the assignments cover for the 2A and 2B, whereas 1A will again just cover the power schematic and how to provide power to your entire board.
Did you say what the workshop?
This Friday. Yeah, this Friday in our IEEE lab, Boulter 2825. Boulter 2825, yeah. You can just also check the IEEE website where it provides information how to get there.
What time Friday?
6 p.m. Oh, I didn't put the time, okay. Yeah, it's at 6 p.m. Alright, thank you so much, guys. Make sure to friend us on Discord if you haven't, and you guys are all free to go. Thank you so much.